Today we're going to be talking about fuzzing. And if somebody is wondering why do you care about fuzzing, I think the easiest answer or example is this list of Go fuzzing trophies. These are the list of bugs that fuzzing has found in the standard library, right? So it's a pretty powerful tool to have in your testing arsenal, and it usually finds things that you wouldn't find in any other way, right? And this is just a list of fuzzing failures that GoFuzzer has found, but there are actually much more that it has found in the Linux kernel, which is a different fuzzing implementation, but yeah. So I guess the main question is like, what is fuzzing? Let me bring up the correct editor. So the simple explanation is that fuzzing is a way to provide randomized inputs to your functions. And what it does, it kind of generates those random inputs. I have written here an equals function that I want to figure out like whether it works correctly or not. And I want to test it with random inputs. But what fuzzing additionally does, it based on the input and what code path it took, it will modify the inputs to try to find new cases and scenarios. So it's not just kind of using completely random inputs, but it's intelligently trying to find interesting inputs for the functions. So how do you use it? So the simple thing is that you define a fuzzing function, let's say fuzz equals, and it's similar to how testing works or test functions work. And then you can add here that an example input for the function, like something like this. So that way this is the initial corpus for the initial examples for the fuzzer to have something interesting to start with, so it doesn't need to completely randomly find it. However, you don't really need it. And finally, and once you have added a few examples, you don't always need them, but it can be useful to make it clear. And then you will write the function where you have arguments for those random inputs that you want here. And of course, these need to exactly match what has been put in here with regards to types. And then you can call the equals function ab, let's say. We don't even need to check whether that makes sense, but we can now run that fuzzing test with fuzz equals. We'll say like which function to run. And also I will set how many concurrent processes I will use, because usually it will use all of your cores, but I don't want to do it while I'm streaming to two different locations and recording my screen. That seems like a recipe for a disaster. So, and now I can try the fuzzing. Once it's, yeah. And as you can see, it immediately failed, right? As a result, you can see here, it also generated a few files. If it's too small, you might not be able to read it, but what's in here is like these both inputs, like, so one is 0 and one is an empty like byte slice. So in some sense, there's one that's like, so it's being run with A is like this, and B is this. So of course the mistake is kind of common. It's that, oh yeah, I forgot to check that A and B are the same length. So if A is not the same length as B, I can just return false. Right. And now I can run the fuzzing again. And of course now you can see that it's spending much more time trying to find new cases and different scenarios. So yeah, does this make sense? Does anybody have questions already?
Yes, one little thing. The fuzz command, is that part of the standard library, or is it something that...
Yes, that's part of the standard library, but it's, you need Go 1.18 for that.
Thank you.
And of course, if it also added this failing scenario into this test data folder, what that means is that now when I run go test, it always runs those failed fuzzing scenarios as well, right? So I cannot reintroduce the same issue with those inputs.
So is it then good practice to like leave that failed result into that test data kind of directory,
Yes.
and commit that part of your project?
Yes, exactly. Because these are just basically 3 test cases for your code, right? And you also have like few other arguments here. One that you already saw, like how much time to spend on fuzzing each of these like inputs, and then the minimization is the like trying to reduce or make the failing scenario smaller. So it's common that the fuzzer will find like a huge an issue with a huge input, but for debugging purposes you want it to be as small as possible, so you or make your test case as simple as possible. Okay. And of course parallel you already saw. So we have fixed one of our functions. Now for our second function, we can also write these. I'm going to write like a testing function for this, but instead of just running the scenario, so I have these 64s here. I can also here check different things. Let's say I want to check that A plus B, or I'll verify that whether like A plus B is the same as B plus A, right? And if it isn't, then we'll fail it, right? Found the case, right? So let's say if B is 0, then return, I don't know, -100. And then we can, let's say, see this in action. So yeah, and you can see that here it found the case. It added it here, and oh yeah, now 0 and 18 has a different result. Like, right. Of course, we can also write more interesting scenarios. So we can check that if both, let's say, A and B are positive, then we definitely know that the result must be bigger than either of the inputs, right? So we kind of negate this result here and see, like, if it, I guess it makes bit easier to read if we do it this way. So if both are positive and the result, I guess, is smaller than either of the inputs, let's write it this way, then yeah, something must be definitely wrong, right? Wrong result, then we'll like add those A, B, result, R. So then we can try this again. And let's see how long it takes to find it. Sometimes it might take a time to find interesting cases. So both are positive, then I might need to help it along so we don't have to wait that long, but so eventually it will, if you use, let's say, something like math, it's something like this here, then we can finally like find it, right? I don't want to wait it here until it finds it, but it will eventually find those. So we can see there's a scenario where if both are positive, we return a negative number, right? So the integer overflows and it fails. So what we want to do with that information, it kind of depends, but here you can see that we can encode these different properties into the test case, and not just kind of like things that we know about the input-output that shouldn't ever fail, right? You could check whether the input is being modified or like, but yeah. Does this make sense? I will currently will disable this test here because I don't know what to do about it. So, any questions?
Yeah, I was wondering like, when you use fast time flags, is there any possibility of false positives, like that it will stop before finding the actual edge cases, or?
By default, it doesn't stop.
But when you use the flags first time,
then it might miss things. So, because it's kind of a randomized process, then it probably doesn't necessarily so it's many companies have like these background workers that are constantly running fuzzing tests, right? So eventually they will discover new things, and
so when would it make sense to use all those timeouts and those timeout flags?
Usually it's more of like, I want to, like, if it cannot find it in an hour, then it's like, maybe it's really difficult to find, right?
Okay. So it's not about putting it into seconds or minutes, but rather like longer period of time.
Yeah, the longer you run, the more likely is it to find issues, right? And I think there have been cases where it has taken several days of fuzzing to find something in the kernel things, but so yeah, like the more complicated your code is, the more fuzzing you want to do, essentially, or longer. Now, of course, you cannot use all the different types for the fuzzer itself. It doesn't support all of them, or arbitrary types, I would say. So currently only these are supported. However, you can write different functions to convert let's say byte slice into a useful type. So I have this dot function which individually multiplies each element and adds up the total, right? And I want to then kind of use that as the use this fuzzing as a fuzzing to test it. But since it doesn't natively support float slices, what I can do is, of course, I'll like I can add a fuzzing function which takes 2 byte slices as input. Right? And then what I can do is then like read out or convert that input into floating point values. So I'm using like read out the little endian 4 bytes for a single float, or 8 bytes for a single float, and then convert it to a float 64, right? And if the bytes length doesn't exactly match 8, then I'll just skip it. Like that's like I don't care about that input, so that way the fuzzer knows a little bit better. And then I can do, let's go like convert this these into like slices of floats, and then I can of course use fuzzing as usual. So I can do, let's say, fuzz dot, and oh no, of course it failed because it also wrote the inputs here, but it's the same case that they aren't the same length. So if they aren't the same, then let's return, I don't know, let's return none. And so, but what we can also do here is do something like mutate. Like previously we swapped around the arguments, but what we can do here is, let's say we reverse the order of elements in those both lists, right? And then we'll check the, so this is the forward, and this is the reversed. And based on like the dot notation or the dot computation, we would expect them to be exactly the same, right? If forward is not the same as reverse, then found failure. Let's do. And this doesn't equal this. So XY and forward and reversed. Okay, let's see. Of course, we found a failure where these aren't like, of course, they returned none, which means that that never equal. So we'll add we'll ignore this for this case. And let's pass a bit more. Did I? Oh. We don't want the NAND result for that check. Let's see whether it will find the interesting case here. Yes, so as we can see, it eventually found a case where if we reverse those slices, the result will be different. So if anybody has, so if we put it here, let's make it bigger. So you can see that the dot product, in one case it was like this 7 point, like it was almost the same. Like you could essentially found a floating point error issue, which isn't always obvious based on this implementation. Like you wouldn't expect if you don't know about floating point error. So it can find these interesting cases that aren't obvious. So yeah, effectively you kind of verify the same thing in multiple ways, and you can then check whether it makes sense. So in this case, what we might want to do is, let's say that if this difference is like less than, I don't know, some small number, then we kind of ignore that. But did I? Oh. Yeah. So then we can like continue fuzzing, and maybe we'll find something more. Anyways, any questions so far? So one common thing that people write is encoding and decoding of data in one form from one format to another. So I have written here two buggy implementations of like encoding this slice of strings as a slice of bytes. So what it does, it kind of converts this the length of the string into this temporary slice, and then it will append to the byte slice, and will append the bytes of the string to the same slice. So it will, in the bytes, will look like, oh, there's a UART encoded length, and then there are bytes for the string. So relatively common. So that's not just length encoded, not run length encoded. And for the decode strings, we do the reverse. We'll take the UART from the data, and then we'll add to the data, right? A relatively common thing. Here, since we don't have a nice way to get the slice of strings, what we can do is instead, let's test 3 strings instead. Like we'll encode with 3 strings and decode 3 strings. So let's do encode strings. So string ABC. And then we can just decode the output to see whether it survived this round trip of encode and decode. So if the slices result decode aren't equal, then we'll like wrong result. So result decode. Oh, this is the string ABC, not the result. So, encoding 3. Decode string. Oh, we also return an error there. And if error, well, then we'll skip. Or then it's failed to decode. Because if it's a round trip, then it never should error. So it immediately failed, of course. So let's see what happened. So we put an empty string, 0, and empty string, right? Then, of course, we can start trying to debug it. We can also like run only that specific test or failure, like it prints out this line here to say that, oh, that's a failing scenario. So we can like debug here. Let's use print lines in this case. So we'll see it like the result here. So we can then see that, oh, it's 33483. But since like we know that the input, so print line, yes. So the input, let's use something clear. And result. So here we can see it, oh, it's an empty string, 0 and empty string, but we shouldn't expect 3 here, right? So there's something wrong here. I already know what the mistake is because I wrote it. So it should have been here, like length of the string, not the length of the input slice. Okay, so just like a regular bug, and then we can see whether, yeah, now it got stuck somewhere. So we can, here we can then we can do here, or data, oh, here. And here we wanted to, since it got stuck here, well, like the debugging part isn't like the important part here, but we can see here that if we put printing here, we can see it got stuck here, and here, since we read 10 bytes, not just like, then we can like fix this bug here to, yeah, if you look into uvarint, it returns the how many bytes it used from this input. And then we can see that it passed, and now we can try fuzzing again. Right. So it will kind of take some try to find new issues here. But we can try the same test as decoding. Let's do decode strings of just random data. Right? This is like what happens if we try to decode random data. So in that case, that's decoding. And of the RS. And of course, let's see, it immediately found an issue. Then it's trying to make a smaller example for me, so it's easier to debug. So, yeah. And we can see here this example. Where was it? So this failed here. So if we try to now, let's see, print this, like what it ended up decoding here, then we can try to see, we want to run this test again. So we can see that it ended up decoding 0 from this data. Let's see what's data at this point. So clearly there's some issue with the data, and if we look into the documentation of uvarint, we see that, oh, there's this case of when this encoding doesn't contain enough information. So we can handle that case now. If let's say n is 0, we can return an error instead. Let's do bad input, or let's do short input. So let's handle that case. Let's see whether we find something more. Oh, import errors. Yeah. That test now passes. Let's see whether we find something more. Of course, we did. And as we can see, we get this out of bounds, and this is due to, like, if we print here the values again, ln data. I should have just run the test, but let's run the specific test. We can see that, oh yeah, the length the string should be is 48, but however, there's not enough data for that string. So we also need to check here if len data is smaller than L, then of course that's also a short input, because before. If you want to try, you can also try this version where you cast it into an int, and whether you find other issues with this. Like, this will also end up being a bug. So you want to cast it into an left side here. And now let's try fuzzing again, and that scenario passes. And yeah, oh, there's now the negative version, like this. It's probably the same issue that, oh, this L is now negative. So, and if, let's say, L is negative, then it's bad input. And, oh, that didn't fix it. So, let's see. This is at line 170. So here. And did we forget to case? Oh, as we can see that, oh, there's a value larger than 64 bits. And this means, oh yeah, well, there's a UR encoded that's not appropriate. So if n is less than small, then we also consider that a bad input. And we can do this.
But
yes.
But you have also the negative check before, right? Yeah.
Yeah, so like either of these, when they are negative, would be like a mistake.
Yeah.
Oh, like L cannot be really negative because it's a uint, so like, that's a meaningless check there. Oh, so let's see whether that works. And yeah, it looks like it's now finally passing. And as you can see, in this short amount of time, we found quite a few bugs that that might be easy to miss, right? Any questions? Okay, I guess we can continue then.
You can also, guys, you can also write in the chat if you feel like want to ask something, then you can also write in the chat.
Yeah. And you might also want to test, let's say, a server. So we have this server that kind of takes a JSON input, some like A and B, and compares the string values here, value at the time, and then we like write output or write whether it was a good result. So that's the server. What we can do is similarly how we did before. Since we cannot do like create complex inputs, we can take these A and B as different arguments here, and then we can try to convert this into a JSON thing, so we can send it to the server, of course. Then we can just skip it if the encoding didn't work. And we can use the HTTP test package for this. We can do like for reading the response, and we can also create a new request for that method. Let's do a method get, and let's pass it body as input to that. And then we can finally call the serve HTTP with those arguments. Of course, if you have written some sort of services, then you can test the services directly and like not have to worry about these response writers and requests. But you can still, like, instead of if you don't want to figure out the exact input, you can also try, let's see what happens if I put completely random input to the sent to the server, like how will it cope with those issues. And then we can do like check that though, whether we get the right result here. So if the result code here isn't if they are equal, then we expect okay, and here wrong result, and case, and otherwise if the result isn't not acceptable, then we expect then we also consider it a wrong result. And yeah, then we can run this fuzz server case. And of course, yeah, we immediately found the same issue that as usual, that when the length isn't the same. So that's not interesting. So let's return this as well here. Let's try again. And yeah, we got the wrong result. Let's see. I didn't. In the case of where's this fuzz server? In the case of these two things, we got the wrong result here. But yeah, I'm not going to bother with like fixing every single mistake here. But this way you can test servers as well, right? Now, any questions about this?
Do you have in production this sort of fuzz tests for servers, or do you simply have the business logic in the server in its own method and you test that?
It depends. I think you want to, it's easier to test the non-server functions, but you can also like there are code generators that I will show in a bit that can yes, Marco, can you put a link to Golang Estonia meetup GitHub?
Yeah, will do.
But yeah, you can fuzz both because they can find issues with let's say like decoding and coding the inputs. But yeah, you kind of need to like figure out like where do I gain the most. Like I found that one of the best cases is like encoding and decoding functions. Like it's the easiest to use there, and it's finds really bizarre cases. However, you can also go further. There are a few different projects that help you generate these functions for you. Let's say I have this map implementation here, which is a concurrent map. We kind of like, when we set the value, we take the lock, and like if we wanted to work without initializing, without needing to initialize it with the constructor, and so we have these few methods, and what we can do is, let's say this fc gen by and we can try generate these fuzzing functions automatically. So let's go to the concurrent map. So if we run this command here, of course you can put it into the code generator that you can easily regenerate those. If I run this generator here, it will then generate this function, right? It will use this special library fuzzer, and it will also create functions for each of these methods for the map. And we can then, here the fuzzer takes also these arguments for like whether you want to call multiple functions in a row, or whether you want to make them parallel. Since this is a concurrent map, I want to test whether the parallelization is okay for that. And then I can call the fuzzer as usual here, go test fuzz, fuzz, and we'll also enable the race detector here. So we'll start to kind of try to find issues. And yeah, of course, it found one. For this fc gen, that's the external tool, you can set this special flag fc debug repro =1. So if you now rerun the test, then it will show what it ended up calling, right? As you can see, it just called this fuzz map get concurrently. So, and if we enable the race detector, then it should point us to the mistake, which is the line 37 here, which is like checking, reading here and writing here for line 38. So as you can see, we have only acquired the read lock, so like multiple gets can might end up concurrently modifying this m.data and causing an issue. To fix it, we can, let's use a sync once to initialize it instead. So let's do function, let's call this init. And then we can fix the implementation and ensure that only one of them can initialize that. And we'll kind of lift it out of the lock, so it doesn't need to use that. And if we rerun the test, of course, then we find that it passes as it, and then we can try, of course, see whether we find anything more. So, yes. And yeah. And this is, yeah, fuzzing. And if you want to read more about it, there are a few links here. So, yeah, that's it.